Hello there, and welcome to Sleepy Science Vault. Somewhere beyond the light of every star you have ever seen with your own eyes, there is a shape, a structure so vast that it takes the entire universe to draw it. We call it the cosmic web. For most of human history, we looked up and saw scattered points of light, and we assumed the universe was simply that, scattered. Random. A sky full of galaxies thrown out into the dark without pattern or design. But as astronomers began mapping the positions of galaxies more carefully, decade after decade, something remarkable started to emerge. The universe was not scattered at all. It had shape. It had structure. It had, in a very real sense, a skeleton. Tonight, we are going to explore that skeleton slowly, one gentle fact at a time, and let the sheer scale of it settle into your mind as you drift toward rest. Let's begin with the idea itself. The cosmic web is the name scientists give to the large-scale structure of the universe, the way that matter, on the very biggest scales imaginable, arranges itself into long threads and wide sheets, separated by enormous empty regions called voids. Imagine, if you can, a structure built not of steel or stone, but of galaxies, billions of them, strung together like glowing beads along threads that stretch across unimaginable distances. That is the cosmic web. Not a metaphor exactly, but a real, physical pattern, traced out by everything we can observe. And here is the first thing worth letting sink in, slowly, in the quiet of this moment. This pattern is not random. When astronomers create maps of galaxies, plotting their positions across huge volumes of space, the galaxies do not spread out evenly, like sugar stirred into water. Instead, they cluster together in certain regions and are almost entirely absent from others. There are long, thin structures dense with galaxies. There are wide, flat structures where galaxies gather like dust settling on a table. And then there are vast, dark regions, whole stretches of space where almost nothing exists at all. The universe, it turns out, has texture. Because of this, scientists often describe the cosmic web as the backbone of the universe. It is the underlying framework that decides where galaxies are allowed to form and where they are not. Just as a skeleton gives shape to a body, determining where the muscles attach and how the whole form holds together, the cosmic web gives shape to the distribution of matter across space. Galaxies did not form in isolation, drifting freely wherever gravity happened to pull them. They formed along this hidden structure, tracing its lines the way frost traces the veins of a leaf. And this brings us to something quietly humbling. Every galaxy you have ever seen in a photograph, every glowing spiral, every soft elliptical smudge of light, is really just a tracer. A marker. A small luminous point revealing the presence of something far larger and far less visible. The galaxies are not the whole story. They are more like streetlights along a highway at night. You can see the lights clearly, and from them you can infer the shape of the road, but the road itself, the vast physical structure connecting everything, extends far beyond what actually shines. So when we look at the cosmic web, we should remember, we are only seeing the illuminated portions of something enormously larger. A hidden network of matter, most of it invisible, threading through the universe in patterns that took billions of years to form. It's worth pausing here, gently, to clarify something important. The cosmic web is not a separate object floating somewhere out in space, distinct from everything else. It is not a single region you could point a telescope toward and say, "There it is." Rather, the cosmic web is the large-scale structure of the universe itself. It is simply the name we give to the overall pattern, the architecture, of how matter is arranged across the cosmos, from the nearest galaxies to the most distant ones we can observe. Wherever there is a universe, in some form, there is a cosmic web. Now that we have this foundation settled, let's look a little closer at what this web is actually made of, because it is more intricate than a simple network of lines. The cosmic web is built from several distinct components, each with its own character. There are filaments, long, thread-like structures of galaxies and gas, stretching across space like glowing rivers in the dark. There are sheets, broader, flatter formations, where matter is gathered across a wider area, somewhat like sprawling wetlands compared to a narrow stream. There are nodes, the densest points in the entire structure, where several filaments converge and enormous amounts of matter accumulate. And finally, there are voids, the vast, mostly empty spaces that occupy far more volume than the structures themselves, silent and dark, holding only a whisper of galaxies compared to their surroundings. Together, these four elements, filaments, sheets, nodes, and voids, form the full architecture of the cosmic web. It is not one shape repeated endlessly, but a layered, varied structure, closer to a living organism's circulatory system than to a simple grid. Let's slow down on the filaments for a moment, because they may be the most poetic part of this entire structure. These filaments act almost like bridges, vast, curving strands of galaxies and diffuse gas that connect one great gathering of matter to another. Picture two immense galaxy clusters, each one a metropolis of hundreds or even thousands of galaxies, separated by hundreds of millions of light years. Between them, a filament stretches like a delicate strand of a spider's web, holding them in gravitational relationship, a bridge spanning distances so large that light itself takes hundreds of millions of years to cross them. Along these filaments, gas flows slowly inward, feeding the galaxies that lie along their length, occasionally sparking the birth of new stars in the quiet dark. In a very real sense, the filaments are not just structural, they are functional. They are the channels through which the universe distributes some of its most essential material. And where do these filaments lead? These filaments meet at points we call nodes. And here, the story becomes especially interesting. Because it is exactly at these intersections, where multiple filaments converge, that we find galaxy clusters, the densest, most massive collections of galaxies in the observable universe. Think of it this way. If filaments are like rivers, then nodes are like the places where rivers meet and pool into vast lakes. All that matter, flowing gently along the filaments over billions of years, eventually gathers at these intersections. Gravity, patient and relentless, pulls everything inward toward the points of greatest convergence. And so galaxy clusters are born, not scattered randomly through space, but positioned with a kind of quiet inevitability, exactly where the cosmic web's threads happen to cross. This is why galaxy clusters tend to sit at the intersections of multiple filaments. It isn't coincidence. It is geometry, playing out on the grandest scale imaginable, a natural consequence of gravity acting on matter across billions of years, drawing everything toward those places where the pull is strongest, where the most filaments meet, and where the most material has had the chance to gather. If you were able to shrink yourself down to the scale of a single galaxy, and drift slowly along one of these filaments toward its node, you would be traveling toward one of the true centers of gravity in the universe. A place where hundreds or even thousands of galaxies orbit one another in a slow, silent dance, bound together by the same quiet cosmic architecture we have been tracing tonight. So already, in just these first 10 facts, a picture begins to form. Somewhere out beyond the edges of what any telescope can fully capture, there exists a vast, invisible framework, filaments stretching like glowing threads, sheets spreading wide and flat, nodes glowing brightly where structures converge, and voids, silent, dark, and enormous, holding the empty space between it all. And scattered along every thread, gathered at every intersection, are the galaxies, trillions of stars each, gathered into luminous points that outline, ever so faintly, the true shape of the universe. Rest here for a moment, in that image, a universe woven together not by chance, but by structure. A hidden lattice, holding galaxies the way a spider's web holds dew in the early morning light, delicate in appearance, yet strong enough to shape the fate of everything within it. In the next part of our journey, we will look more closely at how this remarkable structure came to exist in the first place, tracing its origins back to the earliest moments of the universe, when the first faint patterns of matter began to take shape in the darkness before galaxies, before stars, before light itself had anywhere to shine. For now, let this first understanding settle gently into your mind. The universe is not scattered. It is woven. Between these filaments and their glowing nodes lies something just as important as the structures themselves, the empty spaces. We call these regions cosmic voids, and their scale is almost difficult to hold in the mind. A void can stretch across hundreds of millions of light years, in some cases, over 1 billion. To cross one from edge to edge, even traveling at the speed of light, would take longer than the entire history of human civilization, repeated over and over again. And within these voids, there is very little. A handful of scattered galaxies, drifting alone, far from the crowded filaments and clusters that define the rest of the web. Mostly, there is just space, quiet, dark, and largely undisturbed since the early universe. It is worth sitting with that image for a moment. Vast oceans of near-nothingness, bordered by threads of galaxies so long they seem to stretch toward infinity. The universe is not uniformly full, nor is it uniformly empty. It is a careful, gravitational balance between the two, dense where matter has gathered, and hauntingly empty where it has not. But the cosmic web is not made only of filaments and voids. There are other shapes woven into this vast structure as well, broader, flatter formations known as walls, where galaxies spread out across a wide plane rather than a narrow thread. And there are the node-like cluster regions we touched on earlier, the bright, dense intersections where the greatest concentrations of matter reside. Filaments, walls, nodes, and voids together form the complete architecture of the cosmic web, each one shaped by the same underlying force, each one telling a different part of the same story. And that story begins much further back than you might expect, not with galaxies, not with stars, but with the universe itself in its very first moments. To understand how the cosmic web came to exist, we have to travel back past the formation of every galaxy we have discussed so far, back past the birth of the very first stars, all the way to the beginning. In the earliest instance after the Big Bang, the universe was almost perfectly smooth. Matter and energy were spread out in a hot, dense state, nearly uniform in every direction. Almost uniform, but not quite. Within that near-perfect smoothness, there were tiny variations. Microscopic differences in density, scattered throughout the infant universe, regions ever so slightly denser than their surroundings, and others ever so slightly emptier. These differences were unimaginably small, smaller in relative terms than a ripple on the surface of a still pond. And yet, they were enough. They were the seeds from which everything we have described tonight would eventually grow. Gravity, patient beyond human comprehension, began its slow work almost immediately. Wherever a region was even fractionally denser than its surroundings, gravity pulled a little more matter toward it. That region grew slightly denser still, and so it pulled in even more. Over millions of years, then hundreds of millions, then billions, these tiny initial differences were amplified again and again, growing from near-invisible fluctuations into the vast structures we now recognize as filaments, walls, and clusters. It is a strange thing to consider that the towering structures of the cosmic web, spanning distances that dwarf entire galaxies, trace their origin back to variations so small they would have been imperceptible even to the most sensitive instrument, had anyone been there to measure them. And yet gravity, given enough time, is capable of turning whispers into monuments. This process did not happen quickly. The cosmic web we observe today is the result of billions of years of slow, continuous gravitational growth, a patient unfolding, stretched across nearly the entire history of the universe. The first faint patterns began to emerge within the first few 100 million years after the Big Bang, as gravity started drawing matter toward the slightly denser regions. But it took billions of years more for those patterns to grow into the recognizable web of filaments, sheets, and clusters that fills our galaxy maps today. In many ways, the story of the cosmic web is the story of the universe learning its own shape, slowly, gradually, through nothing more than the quiet, persistent pull of gravity acting again and again across unimaginable spans of time. And it is important to understand that this process has not stopped. The cosmic web is not something that finished forming long ago and now simply sits, unchanged, waiting to be observed. It is still evolving. Even now, gravity continues to pull matter along the filaments, continues to draw galaxies toward the nodes, continues to deepen the voids as matter drains away from them. The structure we see today is simply a snapshot, a single moment captured within an ongoing, billions of years long process that continues even as you rest here, listening. If we could return to observe the universe billions of years from now, the cosmic web would likely look different still. More matter gathered into the nodes. Filaments grown longer, or perhaps merged with neighboring ones. Voids grown even wider and emptier, as gravity continues its long, unhurried work. The cosmic web is less like a finished sculpture, and more like a river delta, constantly reshaped by the same forces that first carved its channels, always changing, even while its overall pattern remains recognizable. Now, having traced its origins, let us turn to a quieter and perhaps more surprising question. What exactly is the cosmic web made of? If you imagine the filaments and clusters of the cosmic web as being built primarily from stars and galaxies, from the glowing matter we can actually observe through telescopes, you would only be seeing a small fraction of the truth. Because most of the mass within the cosmic web is not made of ordinary matter at all. It is made of something else entirely, something we cannot see directly, but whose gravitational influence we can measure with remarkable precision. We call it dark matter. Dark matter does not shine. It does not emit light, or absorb it, or reflect it in any way we have yet been able to detect. And yet, it makes up the overwhelming majority of the mass found within the cosmic web. It is, in a very real sense, the scaffolding upon which everything else is built. The filaments, the nodes, the clusters of galaxies, all of it forms a long pathway shaped first by the gravitational pull of dark matter, with ordinary matter, the gas, the stars, the galaxies we can actually see, following along afterward, gathering within the gravitational wells that dark matter had already carved out. This means that the beautiful, glowing web of galaxies we observe through our telescopes is, in truth, only a faint outline traced upon a much larger, invisible framework. The visible universe, luminous and vast as it seems to us, is really just a thin layer of light resting atop a far greater structure made almost entirely of something we cannot directly see. So the cosmic web is composed of two very different kinds of material, working together. There is normal matter, the protons, neutrons, and electrons that make up stars, planets, gas clouds, and every galaxy we have ever photographed. And there is dark matter, far more abundant, silently dominating the total mass of the structure, shaping its overall form through gravity alone. Ordinary matter provides the light. Dark matter provides the shape. It is a quiet, almost humbling realization that most of what holds the cosmic web together is something we have never seen directly, and may never see directly, no matter how advanced our telescopes become. We know it is there because of how it moves, how it pulls, how it shapes the galaxies and clusters that we can observe. It reveals itself only through its effects, like a wind we cannot see, but whose presence is unmistakable in the way it bends the branches of every tree in the forest. As we continue through this exploration of the cosmic web, this idea will return again and again. The visible universe is a kind of surface, beautiful, intricate, endlessly fascinating, resting atop a deeper, hidden architecture that shapes everything we are able to observe. In the next part of our journey, we will look more closely at the role dark matter plays in shaping the structures we've been discussing, how it forms the invisible scaffolding of the cosmic web, and how astronomers have come to understand its presence despite never having seen it directly. For now, let this quiet truth settle gently into the stillness around you, that the vast, glowing web of galaxies stretching across the universe is only the smallest visible part of something far larger, something silent, unseen, and patiently holding everything in place. We spoke a moment ago about dark matter, that unseen scaffolding shaping the universe from behind the scenes. But let's turn our attention now to the smaller portion, the part of the cosmic web made of ordinary matter, the atoms and particles that make up everything we can actually touch, see, and measure directly. Even within this smaller portion, there is a story worth telling slowly. Ordinary matter in the cosmic web takes several forms. There is gas, drifting in vast and often invisible clouds. There are stars, gathered together into galaxies. And there are the galaxies themselves, the luminous markers we have already spent so much time considering. But together, all of this, every star, every galaxy, every wisp of gas, makes up only a minority of the universe's total matter. A small fraction of the whole, floating within a much larger sea of dark matter that we cannot see at all. Of this small fraction, much of it is not found within galaxies at all. It exists instead within the filaments themselves, spread thin across unimaginable distances. This gas, drifting quietly along the threads of the cosmic web, has a name. Astronomers call it the warm-hot intergalactic medium. It's a curious name when you say it slowly. Warm, hot, intergalactic, medium. For words, each pointing to a different aspect of something strange and diffuse. This gas is warmer than the cold, quiet emptiness of deep space, yet far cooler than the blazing gas found within galaxy clusters. It exists in the vast spaces between galaxies, neither fully part of any single galaxy, nor entirely separate from the larger structure connecting them. And it is diffuse, spread so thin, so faint, that detecting it directly presents one of the great challenges in modern astronomy. Picture something almost like a mist, spread across distances so enormous that entire galaxies could pass through it and barely disturb its structure. That mist is not empty. It carries mass, it carries heat, it carries a quiet trace of the universe's ordinary matter. But its faintness makes it remarkably difficult to observe, hiding in the spaces between the brighter, more obvious structures that first drew astronomers' attention to the cosmic web. And yet, faint as it may be, this warm-hot intergalactic medium may hold an enormous secret. Some studies suggest that it contains a major share, perhaps even the majority, of the universe's ordinary, baryonic matter. Baryonic matter simply means matter made of protons and neutrons, the atoms that build stars, planets, and every living thing. And if much of that matter is hidden away not within galaxies, but within these vast, diffuse filaments of gas stretching across the voids of intergalactic space, then the true distribution of ordinary matter in the universe is far less concentrated in galaxies than it might first appear. Much of it may be quietly drifting along the threads of the cosmic web, present but unseen, waiting patiently within the gas of the filaments themselves. This stands in contrast to another kind of gas found elsewhere in the cosmic web, the gas within galaxy clusters, at the nodes where filaments converge. Here, conditions are dramatically different. Where the gas in filaments is cool and diffuse, spread thin across enormous distances, the gas within galaxy clusters is compressed, energized, and extraordinarily hot, heated by the immense gravitational forces at play as matter falls inward toward these dense cosmic intersections. In fact, this gas within galaxy clusters becomes hot enough to glow, not in visible light, but in X-rays. Where the faint warmth of filament gas resists easy detection, The blazing heat of cluster gas announces itself clearly to instruments designed to observe X-ray radiation. It is one of the quiet ironies of studying the cosmic web. The densest, brightest regions reveal themselves readily, glowing with an intensity we can detect from across the universe, while the vast, subtle threads connecting them remain hidden, whispering rather than shouting, requiring far more delicate methods to uncover. And this brings us gently to one of the great challenges, and one of the great achievements, of modern astronomy. How exactly do we observe something so faint, so diffuse, so quietly hidden as the gas within the cosmic web's filaments? The gas that fills these vast structures does not glow brightly enough on its own to be easily photographed. It is far too diffuse, spread across distances too vast, emitting far too little light to be captured directly by ordinary telescopes. And so astronomers have had to become remarkably resourceful, developing indirect methods, clever techniques, and patient observational strategies to trace the presence of something that resists being seen directly. One of the primary tools astronomers use is the galaxy survey, vast, painstaking projects that map the positions of millions, sometimes billions, of galaxies across enormous volumes of space. By carefully recording where galaxies are located, and just as importantly, where they are absent, astronomers can begin to trace the underlying shape of the cosmic web itself, reconstructing its filaments, its nodes, its voids, based on the visible galaxies that trace its structure. Alongside these galaxy surveys, astronomers also rely on X-ray observations, particularly useful for detecting the hot gas found within galaxy clusters, and increasingly, for revealing fainter structures connecting them. And they rely on something more unexpected, something almost poetic in how it reveals what would otherwise remain hidden. They rely on quasars. A quasar is an extraordinarily bright object, powered by a supermassive black hole actively feeding at the center of a distant galaxy, releasing tremendous amounts of light and energy as matter spirals inward. Quasars are among the brightest objects in the entire universe, so bright that their light can travel across billions of light years, passing directly through the vast, diffuse gas of the cosmic web's filaments along the way. And this is where something remarkable happens. As the light from a distant quasar travels toward us, it passes through any gas that happens to lie along its path, including the faint, diffuse gas of intergalactic filaments. That gas absorbs tiny amounts of the quasar's light, leaving subtle imprints, faint fingerprints within the spectrum of light that eventually reaches our telescopes. By carefully analyzing these imprints, astronomers can detect the presence of gas that would otherwise remain completely invisible, gas far too faint to observe on its own, revealed only because a much brighter light happened to shine directly through it. In this way, quasars act almost like flashlights, held at unimaginable distances, illuminating the darkness that lies between us and them. Each quasar becomes a kind of cosmic backlight, casting its brilliance across billions of light years, revealing the faint silhouette of filamentary gas that would otherwise remain hidden in darkness. It is a beautiful method, if you take a moment to consider it slowly. We are not looking directly at the gas within the filaments. We are looking at the shadow it leaves behind, a subtle absorption, a faint dimming, within the light of something impossibly bright and impossibly distant. Through this shadow, astronomers reconstruct the presence of matter that no telescope could ever photograph directly. And this technique becomes even more powerful when we consider the sheer usefulness of these quasar backlights. Because intergalactic gas is so faint on its own, having a bright background source to illuminate it from behind transforms an otherwise impossible observation into a workable one. Instead of trying to detect something faint against the blackness of space, astronomers instead look for the subtle absence, the quiet dimming, within light that was already bright to begin with. It is, in a sense, easier to notice a shadow crossing a bright light than to notice a faint glow within complete darkness. To gather all of this information, the galaxy surveys, the X-ray observations, the delicate quasar backlighting, astronomers rely on an increasingly sophisticated combination of instruments. Some observations must be made from space, using telescopes positioned above the interference of Earth's atmosphere, particularly important for capturing X-rays, which are largely absorbed before they ever reach the ground. Other observations are conducted using enormous ground-based telescopes, capable of surveying vast areas of sky and cataloging the positions of millions of galaxies with remarkable precision. Each of these instruments reveals a different piece of the same vast puzzle. Space telescopes catch the X-ray glow of galaxy cluster gas, heated to extraordinary temperatures. Ground-based observatories map the positions of galaxies across the sky, tracing the visible skeleton of the cosmic web. And through the careful study of quasar light, astronomers uncover the faint, diffuse gas hidden within the filaments themselves, gas that might otherwise have remained completely undetected, quietly drifting unseen between the galaxies for the entire history of astronomical observation. Piece by piece, method by method, astronomers have slowly assembled a picture of something that cannot be photographed all at once, in a single image, the way we might photograph a distant galaxy or a nearby planet. The cosmic web is not something you simply point a telescope toward and capture in a single frame. It is something reconstructed carefully, patiently, from many different kinds of evidence, gathered across many different instruments, over many years of dedicated observation. And what emerges from all of this effort is nothing short of remarkable, a detailed map, however incomplete, of a structure so vast that it encompasses the entire observable universe. A hidden architecture, traced not through direct sight, but through shadows, through faint X-ray glows, through the careful positions of countless galaxies scattered across the sky. In the next part of our journey, we will look more closely at the nodes of the cosmic web, the galaxy clusters themselves, and explore just how immense, how ancient, and how gravitationally powerful these cosmic intersections truly are. For now, let this thought rest quietly in your mind, that even the things we cannot see directly are not beyond our reach. With patience, with clever methods, and with light borrowed from the most distant and brilliant objects in the universe, even the faintest, most hidden structures can slowly be brought into view. We ended a moment ago with the quiet power of X-ray light, revealing what ordinary vision could never show us. And it is worth lingering there just a little longer, because these X-ray observations have done something particularly extraordinary. They have revealed not just the hot gas glowing within individual galaxy clusters, but the hottest parts of the cosmic web itself, including faint bridges of scorching gas that stretch directly between one cluster and another, connecting these massive nodes across millions of light-years of otherwise empty-seeming space. Imagine two great cities of galaxies, each one blazing with X-ray light, and between them, almost too faint to notice, a thin thread of similarly heated gas, confirming that these two distant structures are not isolated at all, but genuinely connected, joined together by the same filament of the cosmic web that gravity has been shaping since the earliest moments of the universe. These bridges are some of the clearest evidence we have that the cosmic web is not simply a theoretical pattern, inferred indirectly through galaxy positions and subtle shadows in quasar light. It is a real, physical structure, with real, physical gas, hot enough in places to shine in wavelengths our eyes could never perceive. And this leads us into something truly remarkable, a turning point in the story of how we came to understand the cosmic web. Because for a very long time, everything we have discussed tonight, the filaments, the nodes, the diffuse gas, the dark matter scaffolding, remained largely a matter of inference. Astronomers reconstructed the cosmic web through indirect evidence, through statistical patterns in galaxy surveys, through careful analysis of quasar light, through the faint X-ray glow of the hottest gas. It was, in many ways, like assembling a portrait entirely from shadows and reflections, never quite capturing the subject directly in full light. But slowly, that began to change. Some of the earliest direct glimpses of the cosmic web came from observations of cold gas, gas cool enough, and arranged in just the right way, to actually trace the presence of dark matter filaments surrounding distant quasars. In these observations, astronomers were able to detect glowing clouds of gas, extended and elongated, following the same underlying pattern that theory had long predicted for dark matter filaments. It was as though, for the first time, a faint outline of the invisible scaffolding had become visible, not the dark matter itself, which remains undetectable directly, but the gas drawn along its gravitational pathways, glowing softly enough to be captured and studied. What made these observations especially significant was something they revealed almost by accident. The amount of ordinary matter found within these glowing nebulae, these extended clouds of gas tracing the filaments, appeared to be greater than many computer simulations had predicted. It was a small but meaningful discrepancy, the kind of gentle surprise that often points towards something important still waiting to be understood. Perhaps there was more ordinary matter hidden within these filamentary structures than existing models accounted for. Perhaps our simulations, however sophisticated, were still missing something about how gas gathers and glows along the cosmic web's hidden threads. Around this same period, other observations were adding further pieces to the puzzle. The European Space Agency's XMM Newton telescope, an X-ray observatory positioned far above Earth's atmosphere, made a series of detections that would prove especially important. It succeeded in observing hot gas forming a bridge directly between two galaxy clusters, not merely inferred from theory, but directly detected, glowing faintly in X-ray light, exactly where the cosmic web's filaments were expected to connect these two massive structures. This detection mattered enormously, because it helped confirm something that had, until then, remained largely theoretical, that the diffuse gas filling the cosmic web's filaments genuinely does contain ordinary, baryonic matter, present in exactly the diffuse, widely spread form that theory had long predicted. It was no longer only a mathematical inference, drawn from the shadows in quasar spectra. It was a direct detection, glowing faintly across millions of light-years of intergalactic space. Building on this success, a separate and equally significant study combined observations from both XMM Newton and another X-ray observatory, Chandra, to examine a specific structure known as the sculptor wall, a vast, wall-like arrangement of galaxies within the cosmic web, one of many such formations scattered throughout the local universe. Within this structure, astronomers detected the telltale signature of the warm-hot intergalactic medium we discussed earlier, that faint, diffuse gas thought to contain much of the universe's missing ordinary matter. This detection provided some of the strongest evidence yet for a long-standing puzzle in cosmology, the so-called missing baryon problem. For years, careful calculations had suggested that the universe should contain more ordinary matter than astronomers were able to directly account for through visible stars and galaxies alone. Something was missing, unaccounted for, hidden somewhere within the vast structure of the universe. And here, within the hot, diffuse gas of the sculptor wall, astronomers found compelling evidence that at least a significant portion of this missing matter had been there all along, spread thin across the filaments of the cosmic web, too diffuse to detect through ordinary means, yet substantial enough, across such enormous volumes, to account for a meaningful share of the universe's ordinary matter. Piece by piece, these direct detections were transforming the cosmic web from a largely theoretical structure into something increasingly well documented, a structure not just inferred, but observed, measured, and confirmed through multiple independent lines of evidence. And then, more recently, something changed the entire landscape of this research once again, not gradually this time, but rather suddenly, and quite dramatically. New surveys, and new telescopes, began revealing the cosmic web with a level of clarity and detail that earlier instruments simply could not achieve. Structures that had once appeared as faint, blurred smudges, vague suggestions of filaments rather than clearly defined threads, began resolving into sharp, detailed features. Where earlier observations had offered only a rough sketch of the cosmic web's true complexity, these newer instruments began filling in the finer details, the smaller filaments, the subtler connections, the more delicate structures that had simply been beyond the reach of earlier technology. At the center of this transformation stands the James Webb Space Telescope, an instrument whose observations have produced some of the clearest, most detailed maps of the cosmic web ever created. Where earlier surveys, even sophisticated ones, often blurred smaller structures together into single, indistinct features, jwst has been able to resolve these same regions into far greater detail, revealing intricate patterns of filaments and connections that had simply been invisible to previous generations of telescopes. This leap in clarity is especially striking when we compare Webb's observations to those made during the era of the Hubble Space Telescope, long considered one of humanity's greatest astronomical achievements. Hubble's maps of the distant, early universe, while groundbreaking in their own time, often struggled to resolve the finest details of the cosmic web, particularly in its earliest, most distant stages. Webb's maps, by comparison, reveal that same early universe in extraordinary new detail, uncovering filamentary structures that Hubble's instruments simply could not distinguish. Much of this improvement comes down to Webb's remarkable sensitivity to infrared light. As light travels across billions of light-years from the distant, early universe, the ongoing expansion of space stretches its wavelength, shifting it further and further into the infrared portion of the spectrum. This means that some of the most ancient light in the universe, light from the very earliest galaxies, tracing the very earliest formation of the cosmic web, arrives at Earth not as visible light at all, but as faint infrared radiation. Webb, designed specifically to detect this kind of infrared light with extraordinary sensitivity, is able to observe extremely faint, extremely distant galaxies that earlier telescopes, including Hubble, were simply unable to detect. The result has been nothing short of a transformation in how clearly we can see the cosmic web's earliest formation. Structures that once appeared as single, blurred features, their true complexity hidden by the limitations of earlier instruments, are now being resolved into multiple distinct filaments, multiple separate galaxies, multiple individual components, revealing a level of intricate detail that simply did not exist within our observational capabilities only a few years earlier. It is a remarkable thing to consider that our picture of the cosmic web, this vast structure spanning the entire observable universe, continues to sharpen and refine itself, even now, even as you rest here listening. Each new telescope, each new survey, each new method of observation adds a little more detail, a little more clarity, to a portrait that began as the faintest of outlines and continues, patiently, to come into ever sharper focus. In the next part of our journey, we will look more closely at what these newly resolved structures are revealing about the very early universe, and how the cosmic web's earliest filaments came to take shape within the first billion years after the Big Bang. For now, let this quiet realization settle gently over you, that even something as vast and ancient as the cosmic web is still, in a sense, being discovered, coming into focus a little more clearly with each passing year, as our eyes upon the universe continue, slowly and patiently, to improve. This new clarity has done more than simply sharpen the outlines of structures astronomers already suspected were there. It has begun revealing something more subtle, hidden features within the network of galaxies, finer details that had been completely lost within the blur of earlier observations. Where once astronomers could only make out the broad, general shape of a filament or a node, they can now begin to trace its inner structure, small branches, delicate substructures, faint connections between features that had previously seemed separate, but now reveal themselves as part of the same continuous thread. It is a little like finally being able to see the individual branches of a tree, after years of only being able to make out its general silhouette against the sky. The overall shape was always recognizable, but the true intricacy, the fine, delicate detail, had remained hidden, waiting for instruments sensitive enough to capture it. And as this detail has emerged, a broader picture has begun to take shape as well. The universe's large-scale structure, it turns out, appears to be organized with a precision that earlier, blurrier surveys simply could not reveal. Where once the cosmic web seemed like a somewhat loose, approximate pattern, a general tendency for galaxies to cluster in certain areas and avoid others, these newer, sharper maps suggest something more exact. A structure shaped with greater precision, greater consistency, than earlier observations had been capable of showing. The underlying order was always there. We simply needed better eyes to fully perceive it. This growing clarity extends not only across space, but across an even more remarkable dimension, time itself. Because light, as it travels across the universe, carries with it a kind of message from the past. The farther away something is, the longer its light has taken to reach us, and so the further back in time we are actually looking, whenever we observe a sufficiently distant object. This means that by looking deep enough into space, astronomers are not simply seeing distant places. They are seeing distant times, glimpses of the universe as it existed billions of years ago, preserved within the light that has finally, after an almost unimaginable journey, arrived at our telescopes. Using this principle, the newest JWST observations have accomplished something remarkable. They have traced the cosmic web back to a time when the universe itself was only about 1 billion years old, a period so early, so close to the very beginning of everything, that earlier telescopes struggled even to detect individual galaxies from that era, let alone the larger structures connecting them. To place this in perspective, the universe today is approximately 13.8 billion years old. A universe just 1 billion years old represents an early chapter indeed, a time when the very first generations of galaxies were still forming, still gathering along the earliest filaments of the cosmic web, still tracing out, for the very first time, the patterns that would eventually grow into the vast structure we observe today. And now, thanks to Webb's extraordinary sensitivity, astronomers can look directly into that early chapter, and begin to map the cosmic web as it existed during those first formative stages. Much of this remarkable work has come from a particular research effort known as the Cosmos Web Survey, currently the largest survey of its kind conducted using the James Webb Space Telescope, specifically designed to study how the cosmic web has evolved across the enormous span of cosmic history. The scale of this survey is genuinely difficult to comprehend fully. Cosmos Web has been used to trace galaxy structure across an almost unbelievable stretch of time, roughly 13.7 billion years of cosmic history. Nearly the entire lifespan of the universe itself, captured within a single, continuous survey, allowing astronomers to observe not just a single moment in the cosmic web's development, but its entire evolution, from its earliest, faintest beginnings through to the richly structured web we see in the more nearby, more recent universe. What makes this kind of survey so valuable is its ability to place galaxies into increasingly precise slices of cosmic time. Rather than simply observing a broad, general picture of the early universe as a single blurred category, astronomers can now distinguish between different specific eras, comparing what the cosmic web looked like when the universe was 1 billion years old, versus 3 billion years old, versus 7 billion years old, and so on, gradually building a kind of time-lapse portrait of the cosmic web's development, epoch by epoch, across nearly the entire history of the universe. Imagine, for a moment, being able to watch the growth of an ancient forest, not through a single photograph, but through a long sequence of images, each one capturing the forest at a different stage of its growth, a sapling, then a young tree, then a maturing woodland, then finally the dense, established forest we might recognize today. The Cosmos Web Survey offers something remarkably similar for the cosmic web itself, a sequence of cosmic snapshots, each one capturing the structure at a different stage of its long, patient development, allowing astronomers to trace not just what the web looks like now, but how it came to look that way, one epoch at a time. And this extraordinary body of research has not remained locked away within scientific papers and specialized databases. The Cosmos Webb team made a significant portion of their findings publicly available, including a detailed catalog containing information on an astonishing 164,000 galaxies, each one carefully identified, measured, and placed within its proper position in cosmic history. Alongside this catalog, the team also released a video, allowing anyone, not just professional astronomers, but curious minds anywhere in the world, to watch a visual representation of the cosmic web's evolution, unfolding gradually across billions of years, compressed into a single, comprehensible sequence. There is something quietly moving about that, the idea that this vast, almost incomprehensible structure, spanning the entire observable universe and nearly the entire history of time itself, has been made available for anyone to witness, however briefly, however incompletely. A structure once known only through careful inference and subtle shadows in distant starlight can now be watched, in a sense, taking shape, galaxies gathering slowly along filaments, clusters forming at the densest intersections, the entire web gradually thickening and complexifying as billions of years pass by in the span of a short video. As we continue deeper into this exploration, we will look more closely at what these detailed time slices are revealing about the earliest stages of the cosmic web's formation, and how the structures observed in that first billion years compare to the far more developed web we observe much closer to our own time. For now, let this thought settle quietly in the stillness around you, that we are no longer simply imagining the cosmic web's long history. We are watching it, epoch by epoch, as light from across nearly the entire span of cosmic time continues to arrive, patiently, at our telescopes, carrying with it the story of how the universe slowly wove itself into the vast structure we now call home. This growing catalog of galaxies has been made available in a searchable format, meaning that researchers anywhere in the world can explore this deep well of data for themselves, filtering, sorting, and studying particular galaxies or regions of interest without needing to reconstruct the entire survey from scratch. In a field where data has often been scattered, or difficult to access, or locked away within specialized archives, this kind of open availability represents something quietly significant. It transforms an enormous, singular achievement into an ongoing resource, a foundation upon which countless future studies can be built, by researchers who may not have been involved in the original survey at all, yet who can now draw upon its findings freely. And the scale of that foundation is worth pausing on once more. This newest generation of cosmic web maps rests upon one of the largest galaxy samples ever assembled for this particular purpose, roughly 164,000 galaxies, each one carefully catalogued, each one contributing a small piece to our understanding of how matter has organized itself across the history of the universe. It is the kind of number that is almost impossible to hold in the mind all at once. 164,000 individual galaxies, each containing billions of stars of its own, each one a small point of light within the larger tapestry of the cosmic web, and each one now recorded, measured, and made available for study. With a foundation this vast, astronomers have been able to push their observations further back into the past than ever before, back toward the very edge of what is currently possible to observe, into an era so early that it represents, quite literally, some of the youngest structure ever detected in the entire universe. Let us turn our attention there now, to the earliest Webb ever seen. Among the many discoveries to emerge from Webb's extraordinary sensitivity, one finding stands out with particular significance. Astronomers, examining the deep, early universe, identified a thread-like arrangement of 10 galaxies, a small but unmistakable filament, existing at a time when the universe itself was only about 830 million years old. To place that in context, this means we are looking at structure that had already begun forming when the universe was less than 6% of its current age, an almost impossibly early glimpse into the very beginnings of cosmic architecture. 10 galaxies, arranged not randomly, but in a clear, elongated pattern, a filament, in miniature, existing at a time so early that many astronomers had previously wondered whether structures this organized could have formed so soon after the Big Bang at all. And yet, there it was, captured within Webb's extraordinarily sensitive infrared observations, clear evidence that the process of filament formation, the very process we have been tracing throughout this journey, was already well underway less than 1 billion years into the universe's long history. What makes this particular filament even more remarkable is what anchors it. At one end of this thread-like structure lies a luminous quasar, one of those extraordinarily bright objects, powered by a supermassive black hole feeding actively at the center of its galaxy, releasing intense light that can be detected across vast cosmic distances. The presence of this quasar at the heart of such an early filament suggests something intriguing, that these brilliant, energetic objects may serve as markers, helping to identify where some of the very earliest Webb structures happen to form. Wherever a quasar blazes brightly enough to be seen from such an early era, there is a reasonable chance that it sits at the heart of a young, forming node, a place where matter has already begun gathering densely enough to fuel such intense activity, even this early in cosmic history. It is a little like finding a lit lantern in the middle of a vast, dark landscape, and using its glow to help locate the paths and structures nearby that would otherwise remain completely invisible in the surrounding darkness. The quasar's brilliance does not just represent an interesting object on its own. It serves as a marker, a bright anchor point, helping astronomers identify and study the more subtle, harder to detect filament extending outward from it. And the dimensions of this particular filament are worth sitting with for a moment. This early thread of galaxies measured approximately 3 million light-years in length, a genuinely enormous structure, especially when we consider how early it formed. And yet, despite its impressive length, astronomers noted that it was unusually thin for its size, a slender, elongated thread rather than a broad, substantial structure. It stretched impressively across space, while remaining remarkably narrow, almost delicate, in its overall form. This combination, impressive length paired with unusual thinness, offers astronomers valuable clues about how filaments develop over time. It suggests that in these earliest stages, structures may extend outward relatively quickly, establishing their overall length and shape, while the process of thickening, of gathering additional matter, additional galaxies, additional mass along the filament's length, may take considerably longer, unfolding gradually across the billions of years that follow. And this raises a fascinating question, one that naturally follows from everything we have discussed so far. What eventually happens to a filament like this one, so early, so thin, so recently formed? Based on everything astronomers understand about how the cosmic web develops over cosmic time, many researchers expect that at least some of these early filaments are destined to evolve into something far more massive, eventually growing into full galaxy clusters, as more and more matter gathers along their length, as more galaxies form and merge, as gravity continues its long, patient work across the billions of years still to come. It is a remarkable thought to hold quietly in your mind. This slender thread of just 10 galaxies, glimpsed at a moment when the universe itself was still in its infancy, may represent the earliest visible stage of what will eventually become one of the great galaxy clusters of the far future, a bright, dense node within the cosmic web, home to hundreds or even thousands of galaxies, all traced back to this same delicate beginning, captured by Webb at a moment so early that the light we observe today began its journey toward us before most of the universe's present structure had even begun to form. Webb's observations of this early era have revealed something else as well, something related not to the shape of the filament itself, but to the powerful forces already at work within some of the galaxies found along it. Specifically, Webb has provided some of the best evidence yet that powerful quasar winds, intense outflows of energy and material, driven by the same supermassive black holes that power quasars, were already present during this very early period, known to astronomers as the epoch of reionization. These quasar winds appear capable of something quite significant. They can suppress star formation within their host galaxies, pushing gas outward, disrupting the quiet clouds of material that would otherwise slowly collapse to form new stars, effectively acting as a kind of brake on a galaxy's growth, even as that same galaxy's central black hole blazes with tremendous energy. It is a delicate, almost paradoxical relationship, the very process that makes a quasar so brilliant, so powerful, so useful as a marker for early cosmic structure, may simultaneously be limiting the growth of the galaxy that hosts it, blowing outward the very material that galaxy would otherwise use to form new generations of stars. This finding adds another layer of complexity to our understanding of how galaxies and the cosmic web co-evolved during these earliest chapters of cosmic history, a reminder that the story of the cosmic web is not simply about matter gathering peacefully along gravitational pathways, but also about powerful, sometimes disruptive forces, shaping and reshaping that matter even as it comes together for the very first time. From this remarkably early glimpse, let us move forward in cosmic time, toward another discovery, one that represents a genuinely new kind of achievement in the study of the cosmic web. In 2025, astronomers accomplished something that had long been hoped for, but had proven extraordinarily difficult to achieve. They directly imaged a cosmic filament, not inferred through galaxy positions, not reconstructed through statistical analysis, not traced through the subtle shadow of quasar light passing through diffuse gas, but directly observed, captured in an actual image, showing a filament connecting two galaxies that were, at the time, actively forming new stars. This observation captured the universe as it existed approximately 2 billion years after the Big Bang, a somewhat later era than the extraordinarily early filament we just discussed, but still remarkably early in the grand span of cosmic history, still representing a universe considerably younger and less developed than the one we inhabit today. What makes this particular discovery so significant is not just when it occurred, but how it was achieved. This filament was measured at roughly 3 million light-years in length, remarkably similar, as it happens, to the early filament we discussed a moment ago, despite existing at a somewhat later stage of cosmic history. And critically, this structure was not inferred indirectly. It was observed directly, using a specialized instrument known as MUSE, mounted on the Very Large Telescope, a sophisticated ground-based observatory capable of capturing extraordinarily detailed spectroscopic images of faint, distant structures. Direct imaging of a filament, rather than indirect inference through statistical or spectroscopic methods, represents a genuinely significant achievement. It allows astronomers to see, with far greater clarity and confidence, the actual physical connection between two galaxies, an actual bridge of gas and matter, extending across millions of light-years, linking these two actively forming galaxies together within the same segment of the cosmic web. And this kind of direct observation offers something particularly valuable to researchers: the ability to study, with much greater precision, exactly where a galaxy's own gas ends, and where the broader gas of the cosmic web's filament begins. This boundary, subtle and difficult to define, matters enormously for understanding how galaxies grow and evolve. Galaxies do not exist in isolation, sealed off from their surroundings. They draw in gas from the filaments around them, feeding their ongoing formation of new stars, drawing upon the same vast reservoirs of matter that flow slowly along the cosmic web's threads. By directly imaging a filament and the galaxies it connects, astronomers gain a much clearer picture of this exchange, where a galaxy's material ends, and where the larger, shared material of the filament takes over, quietly supplying fuel for the galaxy's continued growth. It is a discovery that brings together so many of the threads, if you will forgive the small play on words, that we have followed throughout tonight's journey. The careful mapping of galaxy positions. The patient study of diffuse, hard-to-detect gas. The powerful capabilities of modern telescopes, both in space and on the ground. All of it converging, in this single achievement, to produce something that would have seemed almost impossible only a few decades earlier: an actual image, an actual direct view, of one of the cosmic web's filaments, captured in the act of connecting two young, actively growing galaxies, billions of years ago, in an era of the universe far younger than our own. As we continue deeper into this exploration, we will look more closely at what these direct images are revealing about the relationship between galaxies and the filaments that feed them, and how this growing body of direct observations continues to transform the cosmic web from a structure once known only through inference, into one increasingly seen, studied, and understood in genuine, direct detail. For now, let this remarkable image rest quietly in your mind: two young galaxies, connected by a slender bridge of gas stretching 3 million light-years across the early universe, captured not through indirect calculation, but through direct light, gathered patiently by an instrument built specifically to see what had, for so long, remained just beyond the reach of human sight. This direct imaging achievement offered something more than just a striking picture. It revealed a process, in motion, unfolding along the length of the filament itself. Gas, astronomers found, does not simply sit still within these structures. It flows, moving slowly along the strands of the cosmic web, drifting from one region to another, carried gently by gravity across millions of light years, connecting galaxies not just visually, but materially, through an ongoing exchange of matter. This particular filament, the one imaged in 2025, turned out to hold an especially interesting detail. The two galaxies it connected were not ordinary in every respect. Both of them hosted supermassive black holes at their centers, immense, gravitationally powerful objects, the same kind of black holes that, in more active states, can power the brilliant quasars we discussed earlier. Here, two such galaxies, each harboring one of these colossal black holes, found themselves linked together by the same slender bridge of gas, extending across the early universe, joining their fates within the same segment of the cosmic web. There is something quietly striking about that image. Two galaxies, each containing an object so massive that light itself cannot escape its gravitational pull, connected not by chance proximity, but by an actual physical structure, a filament of gas, flowing steadily between them, linking two of the most extreme objects the universe can produce, within the gentler, more diffuse architecture of the cosmic web itself. And because this filament could be observed so directly, so clearly, researchers were able to accomplish something that had not been possible before, at least not within this particular system. They were able to separate, with genuine confidence, the gas belonging to each individual galaxy from the gas belonging to the broader cosmic web connecting them. This distinction, subtle as it may sound, matters enormously. It allows astronomers to understand, with much greater precision, where a galaxy's own internal processes end, and where the larger, shared environment of the filament begins, a boundary that had, until this observation, remained difficult to define with any real clarity. For decades, astronomers have built increasingly sophisticated computer simulations, attempting to model how the cosmic web should form and evolve, based on our understanding of gravity, dark matter, and the early universe's initial conditions. These simulations have long predicted certain characteristics, the general shape filaments should take, how they should connect galaxies, how gas should flow along their length. And now, with this new generation of high-definition, directly imaged filaments, astronomers finally have the opportunity to compare theory directly against observation, in a level of detail that was simply unavailable before. The results of that comparison have been quietly reassuring. These new, high-resolution images of cosmic filaments align remarkably well with the predictions of standard cosmological simulations, the same models built from our understanding of dark matter, gravity, and the early universe's initial density fluctuations, the very fluctuations we discussed earlier in tonight's journey. When theory and observation align this closely, it strengthens confidence considerably, suggesting that our broader understanding of how the cosmic web forms and evolves rests on solid foundations, even as new details continue to be uncovered. This same pattern of confirmation has emerged from ground-based observations as well, not just those captured by space telescopes. Recent ground-based imaging has succeeded in resolving a filament with remarkable sharpness and clarity, and once again, the resulting structure matched cosmological simulations with impressive precision. It is a reassuring kind of consistency. Different instruments, different observational techniques, different research teams, all converging on results that align closely with the same underlying theoretical framework, developed patiently over decades of careful scientific work. Having explored some of these individual, remarkable discoveries, let us step back now and consider the broader methods astronomers use to study the cosmic web as a whole, the frameworks, the classifications, and the analytical tools that allow scientists to make sense of something so vast, so complex, and so intricately structured. One important way of understanding the cosmic web involves studying its dynamics, not simply its shape, frozen in a single moment, but the forces and strains actively at work within it. Filaments, walls, clusters, and voids are not static, unchanging features. They exist within a constant interplay of gravitational forces, matter flowing along filaments, gas falling into clusters, and voids slowly expanding as matter drains away from them toward denser regions. By studying these dynamics, the actual physical forces shaping each component of the web, astronomers gain a much richer understanding of not just what the cosmic web looks like, but why it takes the particular form it does, and how it continues to change over time. To help organize and classify this immense complexity, researchers have developed formal analytical frameworks, structured methods for categorizing different regions of the cosmic web based on their particular characteristics. One such method is known as the T-Web statistical description, a formal approach that allows astronomers to classify cosmic structure systematically, distinguishing between filaments, walls, nodes, and voids based on specific, measurable mathematical properties, rather than relying solely on visual impression or general description. This kind of formal classification matters a great deal in modern astronomy. When researchers around the world are studying vast datasets, containing millions of galaxies spread across enormous volumes of space, having a consistent, mathematically grounded method for identifying different structural components allows for meaningful comparison between different studies, different surveys, and different regions of the universe. Without such frameworks, the subtle, subjective differences in how one researcher might define a filament versus another could introduce confusion and inconsistency into the broader scientific understanding of the cosmic web. Building upon these classification methods, researchers have also worked to develop what are known as filament catalogs, comprehensive lists, carefully compiled, identifying and describing individual filaments across large volumes of observational data. Creating these catalogs accurately requires careful calibration, grounded in genuine physical understanding of how filaments actually form and behave, rather than relying on overly simplistic or purely visual methods of identification. By calibrating these methods carefully, astronomers can improve the accuracy and consistency with which filaments are identified within complex, often noisy observational data, ensuring that what gets labeled as a filament in one dataset would be recognized similarly in another, maintaining consistency across the broader scientific effort to map the cosmic web. Perhaps most fascinating among these methodological advances is the growing ability to track individual filaments across different epochs of cosmic time, rather than simply studying filaments as a general population, observed at a single moment, frozen within one particular era of the universe's history. This kind of tracking allows astronomers to follow the actual life story of a specific structure, watching how an individual filament changes, develops, and evolves across billions of years, rather than only comparing broad statistical patterns between different populations of filaments observed at different times. It is, in a sense, similar to the difference between studying a general population of trees at different ages versus following one particular tree from seedling to maturity, observing its individual growth and development over its entire lifetime. Both approaches offer valuable insight, but tracking individual structures across time provides a uniquely detailed, continuous narrative, a genuine developmental history, rather than a series of separate snapshots. And through this kind of careful, individualized tracking, astronomers have discovered that filament properties can vary quite dramatically, depending on their surrounding environment. Not every filament follows the same path of development. Some filaments, particularly those located within especially dense regions of the cosmic web, tend to collapse over time, gradually contracting, feeding matter inward toward nearby nodes, eventually losing their distinct filamentary shape as they merge more fully into the surrounding cluster structure. Other filaments, however, particularly those situated closer to the vast emptiness of cosmic voids, tend to expand instead, stretching gradually outward over time, growing longer and more diffuse as the surrounding void continues its slow expansion, pulling matter thin across an ever-increasing volume of space. This environmental variation adds another layer of richness to our understanding of the cosmic web structure. It is not a uniform, evenly behaving network, where every filament follows an identical pattern of development. Rather, it is a complex, environmentally sensitive structure, where a filament's fate, whether it will collapse inward toward a growing cluster or stretch outward into an expanding void, depends significantly on its particular location within the broader architecture of the web. As we continue moving deeper into this exploration, we will look more closely at how astronomers use these various analytical tools together, combining dynamical studies, formal classification methods, carefully calibrated catalogs, and long-term tracking of individual structures, to build an increasingly comprehensive, increasingly precise understanding of the cosmic web's true complexity. For now, let this quiet complexity settle gently into your thoughts, a structure where gas flows steadily between distant galaxies, where individual filaments can be followed patiently across billions of years of cosmic history, and where the same underlying network behaves differently depending on where, within its vast architecture, a particular thread happens to lie, collapsing here, expanding there, each filament following its own quiet, gravitational path through the long unfolding story of the universe. We spoke a moment ago about how filaments can behave so differently depending on their environment, some collapsing, some stretching outward. It's worth pausing on just how vast a range this diversity actually spans. Within computer simulations, designed to model the cosmic web's development across billions of years, astronomers have found filaments of truly staggering variety and length. Some of the longest filaments identified within these simulations extend beyond 100 megaparsecs, a distance so large that it becomes genuinely difficult to hold in the imagination. A single megaparsec is already equivalent to over 3 million light-years. 100 megaparsecs, then, represents a structure stretching across hundreds of millions of light-years, a single, continuous filament, vastly larger than the shortest filaments found within the same simulations, which may measure only a small fraction of that length. This enormous range reminds us, once again, that the cosmic web is not a uniform lattice, built from identical, repeating units. It is something closer to a living, organic structure, filled with variation, some threads modest and short, others sprawling across distances that dwarf entire galaxy clusters, each one shaped by its own particular history of gravitational growth. And yet, despite this remarkable diversity, something quietly reassuring has also emerged from this research. Even amid such wide variation in individual filament length and behavior, certain global properties of the cosmic web as a whole appear surprisingly stable over enormous stretches of cosmic time. While individual filaments may grow, shrink, collapse, or expand according to their particular local environment, the broader statistical characteristics of the cosmic web, its overall proportions, its general balance between filaments, walls, nodes, and voids, tend to remain remarkably consistent across billions of years. It is a delicate balance between constant local change and persistent overall stability, individual threads shifting and evolving, while the larger tapestry they form together retains a recognizable, consistent character across almost the entire history of the universe. Having explored the cosmic web structure, its history, and the methods used to study it, let us turn now to a particularly important question, one that moves beyond simply describing the cosmic web, and begins asking what it actually does. How does this vast structure influence the galaxies living within it? How does it shape their growth, their development, their very evolution across cosmic time? This question sits at the heart of some of the most active current research into the cosmic web. Increasingly, astronomers are using this vast structure not simply as an interesting pattern to observe and map, but as a genuine tool for understanding galactic evolution itself, particularly focusing on how a galaxy's supply of gas, drawn from its surrounding environment, influences the way it grows and changes over billions of years. Because here is something important to understand about the cosmic web, beyond its role as simply a beautiful, large-scale pattern stretched across the universe. It is not merely filaments existing quietly in otherwise empty space, disconnected from the galaxies scattered along their length. Rather, the cosmic web functions as an active environment, a surrounding context that directly shapes how individual galaxies gain new gas, or, in some cases, lose the gas they already have. A galaxy's location within the cosmic web, whether nestled within a dense filament, positioned near a bustling node, or drifting in relative isolation within a vast, empty void, genuinely influences the resources available to that galaxy for continued growth. This influence becomes especially clear when astronomers compare galaxies found in different regions of the cosmic web. Galaxies located within filaments, and within the smaller, more delicate structures sometimes called tendrils, tend to show certain distinct characteristics. They often display higher metallicities, meaning their gas contains a greater proportion of heavier elements, elements formed through previous generations of stars, then released back into the surrounding gas through stellar processes. At the same time, these filament-dwelling galaxies tend to show somewhat lower star formation rates compared to galaxies found elsewhere, forming new stars a little more slowly, a little more gradually, than some of their more isolated counterparts. This pattern makes a certain intuitive sense. once we consider what we've already learned about the cosmic web structure. Galaxies within filaments exist within a busier, more crowded environment, closer to other galaxies, closer to the gas that has already been processed through earlier generations of star formation. Their surrounding gas has, in a sense, already been used before, enriched by previous stellar activity, carrying the leftover chemical traces of stars that lived and died long before the current generation of star formation began. This enriched, somewhat used gas contributes to higher metallicity, while also, perhaps, providing slightly less efficient fuel for forming entirely new generations of stars. Void galaxies, by contrast, those relatively rare galaxies found drifting within the vast, largely empty spaces between filaments, tell a somewhat different story. These isolated galaxies often continue forming stars quite efficiently, maintaining relatively high star formation rates despite their apparent isolation. The reason for this may lie in the particular character of the gas available to them. Because void galaxies exist in relatively undisturbed, isolated surroundings, far from the busier, more processed environment of filaments and clusters, they may have access to colder, less previously processed gas that has not yet been heated, enriched, or otherwise altered by extensive prior stellar activity. This colder, fresher gas can prove particularly effective fuel for ongoing star formation, allowing void galaxies to continue growing steadily, even in the relative quiet of their isolated cosmic surroundings. There is something almost poetic in this contrast. The busier, more crowded regions of the cosmic web, the filaments, the nodes, the walls, offer galaxies a rich environment, filled with gas, other galaxies, and gravitational interaction, yet this same richness comes with a kind of used, previously processed quality that can gently slow the pace of new star formation. The quiet, isolated voids, meanwhile, though nearly empty of galaxies and structure, offer their rare inhabitants a kind of pristine simplicity, fresh, cold, undisturbed gas, allowing star formation to continue at a steady, efficient pace, undisturbed by the crowded chemistry of busier cosmic neighborhoods. And the cosmic web's influence over its galaxies may extend even further than gas supply and star formation rates. One particularly intriguing recent discovery suggests that filaments may influence something even more fundamental to a galaxy's basic character, its spin. Some research has found evidence suggesting that galaxies may actually rotate in a way that is subtly synchronized with the larger filamentary structure surrounding them, as though the broader gravitational architecture of the cosmic web leaves a quiet imprint, not just on a galaxy's gas supply or its rate of star formation, but on the very direction and character of its rotation. This is a remarkable thought to consider slowly. It suggests that a galaxy's identity, in some deep sense, may be shaped not only by its own internal processes, its own stars and gas and dark matter, but also by the vast, surrounding structure of the cosmic web itself, as though each galaxy carries, within its own rotation, a subtle echo of the larger gravitational pattern that shaped its formation and continues to influence its ongoing evolution. Let us turn, finally, in this segment, to one of the most significant scientific achievements to emerge from this growing body of cosmic web research, the resolution, or at least the substantial progress toward resolving, one of astronomy's most persistent and puzzling questions. We touched earlier on what astronomers call the missing baryon problem, the long-standing puzzle surrounding the apparent absence of a significant portion of the universe's ordinary, baryonic matter. For years, careful calculations, based on our understanding of the early universe and the process of Big Bang nucleosynthesis, suggested that the universe should contain considerably more ordinary matter than astronomers were able to directly account for through visible stars, galaxies, and detectable gas clouds. A significant portion of the universe's expected matter seemed to be missing, unaccounted for, hidden somewhere beyond the reach of existing observational methods. Recent research, building on many of the discoveries we have discussed throughout tonight's journey, suggests an increasingly compelling answer to this long-standing mystery. The cosmic web itself, and specifically the warm-hot intergalactic medium, that faint, diffuse gas spread thin along the filaments connecting galaxies, may be exactly where much of this missing ordinary matter has been quietly residing all along. This growing body of evidence has led astronomers to reconsider how they think about the cosmic web's fundamental role within the universe. It is no longer understood simply as a structure that determines where galaxies form and cluster together. It is now considered something more, a genuine reservoir, holding within its vast, diffuse filaments a substantial portion of the universe's so-called missing baryons, ordinary matter that had long been theoretically predicted, yet had remained frustratingly difficult to directly detect, scattered too thinly across too vast a volume of space to be easily observed through conventional methods. And the progress made in confirming this understanding has been genuinely significant. Through the combined efforts of galaxy surveys, X-ray observations, quasar backlighting techniques, and increasingly detailed direct imaging, astronomers have now succeeded in locating approximately half of the universe's previously missing normal matter, found not within galaxies themselves, but within the vast, quiet spaces of intergalactic space, distributed thinly along the filaments of the cosmic web. Half. It is worth letting that number settle slowly into your thoughts. For years, this matter remained entirely unaccounted for, a genuine puzzle troubling cosmologists studying the fundamental composition of the universe. And now, through patient, careful, increasingly sophisticated observation, through quasar light passing through invisible gas, through the faint X-ray glow of superheated filaments, through direct imaging capturing actual bridges of matter stretching between distant galaxies, roughly half of that missing matter has finally been located, quietly residing within the same vast, diffuse structure we have spent this entire journey exploring together. It is a remarkable resolution to a genuinely difficult scientific mystery, not a sudden, dramatic breakthrough, but rather the patient accumulation of evidence, gathered gradually across years of careful observation, each new discovery adding another small piece to an increasingly complete picture. The missing matter was never truly missing at all. It was simply hidden, spread thin across unimaginable distances, drifting quietly within the same cosmic web that connects every galaxy, every cluster, every corner of the observable universe. As we continue toward the final chapters of this exploration, we will look more closely at what remains to be discovered, the portion of missing matter still unaccounted for, and the questions that continue to guide astronomers as they refine their understanding of this vast, quietly essential structure. For now, let this remarkable resolution settle gently into the stillness around you, that even the universe's most persistent mysteries, its most stubbornly hidden secrets, can slowly, patiently, be brought into the light, not all at once, but piece by piece, half by half, through the quiet, persistent effort of careful observation, stretched patiently across years of dedicated scientific work. This missing matter, now located, belongs to something astronomers call the intergalactic medium, a term that, once you slow down and consider it fully, describes something almost breathtaking in scope. This medium is not confined to galaxies, not gathered neatly within the bright, familiar structures we can easily photograph. It extends, in one form or another, essentially throughout all of space, filling the vast distances between galaxies, threading quietly through filaments, drifting gently within the outskirts of clusters, present almost everywhere, even in regions that might, at first glance, appear entirely empty. Within this intergalactic medium lies the particular component we discussed earlier, the warm-hot intergalactic medium, often referred to simply by its initials, WIM. This diffuse, difficult-to-detect gas is now thought to hold a substantial share of the universe's missing baryons, and importantly, it has only relatively recently become detectable in any real, meaningful detail. For a long time, this gas existed primarily as a theoretical prediction, a plausible explanation awaiting confirmation. Only through the patient accumulation of increasingly sophisticated observational techniques, the very techniques we have traced throughout tonight's journey, has this elusive gas finally begun revealing itself with genuine clarity. And among these techniques, one particularly clever method deserves special attention, a method that might, at first, seem to have little to do with diffuse intergalactic gas at all. Astronomers have begun using something called fast radio bursts, brief, extraordinarily intense flashes of radio energy, originating from distant sources scattered across the universe, as a tool for probing the otherwise invisible matter lying between galaxies. The logic behind this method carries a certain quiet elegance. As the radio waves from a fast radio burst travel across the universe, on their way toward our telescopes, they pass through any matter that happens to lie along their path, including the faint, diffuse gas of the intergalactic medium. This intervening matter subtly affects the radio signal, causing different wavelengths within the burst to arrive at very slightly different times, a phenomenon that allows astronomers to measure, with surprising precision, how much matter the signal passed through on its long journey toward Earth. It is, in many ways, conceptually similar to the quasar backlighting technique we discussed earlier, using a bright, distant signal to reveal the presence of matter that would otherwise remain completely invisible. Except here, instead of light being absorbed by intervening gas, it is the arrival timing of radio waves that carries the crucial information, subtly delayed by whatever diffused matter happened to lie somewhere along the vast distance between the burst's origin and our own instruments. Using this remarkable technique, a study conducted in 2025 was able to partition the universe's missing baryons with a level of precision that had not previously been achieved. Rather than simply confirming that missing matter existed somewhere within the intergalactic medium, this research began mapping out, with much greater specificity, exactly how that matter was distributed across the different components of the cosmic web. A separate study, also making use of fast radio bursts, arrived at a particularly striking figure. This research found that approximately 76% of the universe's baryonic matter, the ordinary matter made of protons and neutrons, the material that forms stars, planets, and everything tangible we might ever encounter, resides within the intergalactic medium itself. Not within galaxies. Not within the bright, familiar structures we typically associate with the universe in casual conversation, but rather, drifting quietly within the vast spaces between galaxies, spread thin across the filaments and voids of the cosmic web. Let that figure settle slowly into your thoughts. 76%. 3/4 of all the ordinary matter in the universe, existing not within the galaxies that first drew our attention to the night sky, but within the far vaster, far quieter spaces surrounding them. The stars, the planets, every galaxy we have ever photographed, all of this represents only a modest fraction of the universe's total ordinary matter. The overwhelming majority resides instead within this diffuse, largely invisible medium, patiently distributed across the cosmic web's enormous structure. This same research effort also examined where the remaining baryonic matter could be found. Approximately 15%, the study estimated, resides within galaxy halos, the extended, diffuse regions of gas and matter surrounding galaxies, reaching beyond their visible edges, yet still gravitationally bound to them. This leaves only a comparatively small fraction of the universe's ordinary matter located within stars themselves, or within the colder, denser gas found more directly within galaxies' visible structures, the very matter that forms the stars, planets, and luminous features we typically imagine when picturing the contents of the universe. It is a genuinely humbling recalibration, when you consider it slowly. The glowing galaxies, the brilliant stars, everything we can see clearly through even our most powerful telescopes, represents only a small portion of the universe's total ordinary matter. The vast majority exists instead in forms far less visible, far more diffuse, scattered across distances so enormous that direct detection required decades of technological advancement, and methods as creative as measuring subtle delays in the arrival of distant radio bursts. And within this broader picture, recent measurements have added yet another layer of detail, specifically addressing the role of cosmic voids, those vast, largely empty regions we discussed earlier in tonight's exploration. According to these newer findings, approximately 20% of the universe's baryonic matter may reside within the voids themselves, the spaces between the web-like filaments, historically considered nearly empty, yet apparently containing a meaningful share of the universe's ordinary matter after all. This finding adds welcome nuance to our understanding of cosmic voids. While they remain, by any reasonable definition, far emptier than the surrounding filaments, walls, and nodes of the cosmic web, they are not entirely devoid of matter. A meaningful portion of the universe's missing baryons appears to drift even within these vast, quiet regions, present, but so thinly spread, so diffusely distributed, that detecting it required exactly the kind of sophisticated, indirect methods we have spent this journey exploring together. Finally, it's worth pausing to appreciate just how extraordinarily diffuse this missing matter truly is, wherever within the cosmic web it happens to reside. These missing baryons exist at densities below 1 particle per 1,000 cubic centimeters, an almost unimaginably sparse distribution, far thinner than what we would typically consider even a very good vacuum here on Earth. And beyond simply being sparse, this gas is also highly ionized, meaning its atoms have been stripped of their electrons, existing not as complete, stable atoms, but as charged particles, drifting individually through the vast emptiness of intergalactic space. This extreme diffuseness helps explain why this matter remained undetected for so long, despite representing such a substantial portion of the universe's total ordinary matter. Gas this thin, this sparse, this widely dispersed across such enormous volumes of space, simply does not glow brightly, does not absorb light dramatically, does not announce its presence through any of the more obvious observational signatures astronomers might typically rely upon. It required patient, creative, increasingly sophisticated methods, quasar backlighting, X-ray detection of the hottest regions, and now, the subtle timing delays within fast radio bursts, to finally reveal a resource that had, in truth, been there all along, quietly filling the vast spaces of the cosmic web since the earliest chapters of cosmic history. As we move toward the closing chapters of this long, patient journey through the cosmic web, we carry with us this remarkable understanding that the universe's ordinary matter, the very stuff of stars and planets and everything we have ever known, exists overwhelmingly not within the bright, familiar structures we can easily see, but within the vast, quiet, diffuse spaces connecting them, hidden in plain sight, waiting patiently across billions of years, for methods delicate enough, and patient enough, to finally bring it into view. For now, let this quiet vastness settle gently around you, 3/4 of all the ordinary matter in the universe, drifting invisibly between the galaxies, filling the filaments and voids of the cosmic web in a form so diffuse, so thinly spread, that it remained hidden from us until only the most recent chapter of our long human effort to understand the universe we call home. These observations of hot, faint threads stretching across intergalactic space carry significance that reaches far beyond the individual discoveries themselves. Each one contributes to a larger, unfolding resolution of that long-standing missing matter problem we have followed throughout this journey. By locating baryonic matter within these faint, diffuse filaments, matter that had, for so long, eluded direct detection, astronomers move closer, observation by observation, to a complete accounting of the universe's ordinary matter, tracing it patiently back to the vast, quiet threads of the cosmic web where it has resided all along. And increasingly, the evidence gathered through these methods is converging with theory in a way that offers genuine scientific satisfaction. Some of the most recent studies examining the distribution of baryons throughout the cosmic web have found that this distribution strongly matches what cosmological simulations predicted, often years or even decades earlier. This alignment between careful theoretical modeling and hard-won observational evidence represents one of the quieter triumphs of modern astronomy, a confirmation that our fundamental understanding of how matter distributes itself across the universe rests on solid ground, built from principles that have now been tested against the increasingly detailed observations we have spent this journey exploring together. This growing agreement extends to another important aspect of the cosmic web story as well, the relationship between galaxies and the surrounding intergalactic medium. Simulations and observations now align more closely than ever before in showing that strong feedback processes from galaxies, the outward flows of energy and material we touched upon earlier, driven by processes like quasar winds and vigorous star formation, actively enrich the intergalactic medium surrounding them. Galaxies, it seems, do not simply draw matter inward from their surroundings. They also give something back, releasing processed material outward into the diffuse gas of the cosmic web, subtly altering its composition across enormous volumes of space. Theory predicted this exchange. Observation has now confirmed it, quietly and convincingly, across an increasing number of studied systems. With this foundation of confirmed understanding beneath us, let us turn now to some of the most extraordinary structures yet discovered within the cosmic web, structures so immense that they stretch the very limits of what the word large can meaningfully describe. In a study reported in 2026, astronomers identified something remarkable within the Shapley supercluster, one of the most massive concentrations of galaxies known within the relatively nearby universe. There, researchers detected a filament of hot gas, linking together not two galaxy clusters, as in earlier discoveries we discussed, but four separate galaxy clusters at once, a single, continuous thread of superheated material, weaving its way across an almost unfathomable distance of approximately 23 million light-years. 23 million light-years. It is worth allowing that number to rest quietly in your mind for a moment, because our own galaxy, the Milky Way, spans roughly 100,000 light-years from edge to edge. This single filament, then, stretches across a distance more than 200 times the width of our entire galaxy, a single connected structure, linking four massive clusters of galaxies into one continuous gravitational and thermal system. And the mass contained within this extraordinary structure proves equally difficult to comprehend fully. This hot filament was found to contain roughly 10 times the mass of the Milky Way itself, meaning that within this single thread of diffuse, superheated gas, stretched across 23 million light-years of intergalactic space, there exists enough matter to build 10 galaxies the size of our own, if that matter were ever gathered together into such a form. Instead, it remains spread thin, glowing faintly in X-ray light, quietly connecting four separate galaxy clusters within one of the largest known structures in our cosmic neighborhood. Discoveries like this remind us just how much remains to be found within the cosmic web, even after decades of careful study. Structures of this scale, this mass, this significance, continue to reveal themselves as our instruments grow more sensitive, our methods more refined, our understanding of where and how to look more sophisticated with each passing year. As we approach the closing chapter of this long journey together, let us turn our attention toward the future, toward the questions that continue to guide astronomers as they refine their understanding of this vast, patient structure connecting the entire observable universe. One of the most important roles the cosmic web now plays within modern astronomy extends beyond simply describing where galaxies are located, or how matter has organized itself across cosmic history. Increasingly, scientists use the cosmic web itself as a tool, a way of testing our broader understanding of the universe's fundamental workings. This is possible because the shape, the scale, and the ongoing growth of the cosmic web depend directly on some of the most fundamental forces and processes governing the entire universe: gravity, the mysterious influence of dark matter, and the universe's long history of cosmic expansion. If our theoretical models of these fundamental processes are correct, then the cosmic web should take on a very particular form, following very particular patterns of growth across cosmic time. And so, by carefully observing the actual cosmic web, its filaments, its nodes, its voids, its rate of growth across billions of years, astronomers gain a powerful means of testing whether our broader theories about gravity, dark matter, and cosmic expansion truly hold up against the observable universe. The cosmic web, in this sense, becomes something more than simply an interesting structure to study for its own sake. It becomes a kind of grand natural experiment, patiently unfolding across billions of years, offering astronomers a way to check their deepest theories about how the universe actually works. Among the most recent contributions to this ongoing effort, a particularly significant achievement involves the direct mapping of dark matter itself, using observations from the James Webb Space Telescope. This recent work succeeded in tracing the invisible mass of dark matter across a region of sky measuring about 0.54 square degrees, located within the constellation Sextans, a relatively modest patch of sky, yet one that yielded remarkably detailed results. This dark matter map achieved a resolution of approximately 1 arc-minute, a level of detail sharper than earlier space-based dark matter maps had been able to achieve. To place this in perspective, an arc-minute represents an extraordinarily small angular measurement, roughly equivalent to the width of a single human hair, viewed from about 10 meters away. Achieving this level of resolution while mapping something as fundamentally invisible as dark matter represents a genuinely remarkable technical achievement, allowing astronomers to trace the presence and distribution of dark matter with a clarity that simply was not possible using earlier instruments and methods. And what this detailed map revealed aligns beautifully with everything we have explored together throughout this long journey. The map showed dense clumps of dark matter, concentrated in particular regions, connected together by fainter, more extended filaments, a pattern that closely matches the visible cosmic web we can observe directly through the positions and distributions of galaxies. The invisible scaffolding of dark matter, and the visible tracery of galaxies that follow along its gravitational pathways, align with remarkable precision, confirming, through direct, detailed observation, the fundamental relationship we discussed earlier in this journey, between the hidden mass that shapes the universe's structure, and the luminous matter that traces its outline for us to see. This finding carries with it a particularly meaningful conclusion, one that brings together so many of the threads we have followed throughout tonight's exploration. This detailed dark matter map demonstrates clearly that dark matter and ordinary matter did not develop separately, along entirely different, unconnected paths. Rather, they grew together, in careful gravitational partnership, across billions of years, jointly constructing the cosmic web we have spent this entire journey coming to understand. The invisible scaffolding of dark matter provided the underlying gravitational structure, while ordinary matter, drawn along by that same gravitational influence, gathered gradually into the stars, galaxies, and diffuse intergalactic gas that trace the web's true shape for us to observe. And so, as we arrive at the end of this long, patient journey through the cosmic web, let us gather together, gently, everything we have discovered along the way. We began with a simple but profound realization that the universe is not scattered randomly across space, but woven instead into a vast, interconnected structure of filaments, walls, nodes, and voids. We trace this structure back to its earliest origins, to the tiny, almost imperceptible fluctuations present within the universe's first moments, patiently amplified by gravity across billions of years into the vast architecture we observe today. We explored what this structure is truly made of, learning that dark matter, invisible and undetectable directly, provides the gravitational scaffolding upon which everything else depends, while ordinary matter, the atoms and gas and stars we can actually observe, follows along, tracing only a faint outline of something far larger and more hidden. We followed the remarkable story of how astronomers learned to observe this hidden structure, through galaxy surveys mapping the visible skeleton of the web, through the faint shadows cast by quasar light passing through invisible gas, through the blazing X-ray glow of the hottest intergalactic bridges, and finally, through direct imaging, capturing actual filaments connecting actual galaxies, glowing softly across millions of light-years of otherwise empty-seeming space. We traveled back to the very earliest chapters of cosmic history, glimpsing filaments already forming when the universe itself was less than 1 billion years old, anchored by brilliant quasars, destined perhaps to grow into the massive galaxy clusters of the much later universe. We watched as new telescopes, particularly the James Webb Space Telescope, transformed our understanding almost overnight, resolving blurred, uncertain structures into sharp, detailed portraits of the cosmic web's true complexity, both in the present universe and across nearly its entire cosmic history. We discovered that this vast structure does far more than simply hold galaxies in place. It actively shapes their evolution, determining their gas supply, influencing their rate of star formation, perhaps even subtly guiding the very direction of their rotation. Galaxies within busy filaments grow differently than those drifting quietly within cosmic voids, their development shaped, in ways both obvious and subtle, by their particular position within this grand architecture. And perhaps most remarkably, we followed the patient resolution of one of astronomy's most persistent mysteries, the long search for the universe's missing ordinary matter. Through quasar backlighting, through X-ray observation, through the ingenious use of fast radio bursts, astronomers gradually located this missing matter, not absent from the universe at all, but simply hidden, spread thin across the vast, diffuse filaments and voids of the cosmic web, present in quantities that account for the overwhelming majority of all ordinary matter in existence. We witnessed structures of almost incomprehensible scale, a single filament stretching 23 million light-years, linking 4 massive galaxy clusters together, containing enough mass to build 10 galaxies the size of our own. And we closed with one of the most elegant confirmations yet achieved, a detailed map of dark matter itself, revealing, with remarkable clarity, that the invisible and the visible, the hidden scaffolding and the luminous galaxies it supports, grew together, in patient gravitational partnership, across the entire span of cosmic history. This is the cosmic web. Not simply a scientific curiosity, confined to research papers and specialized journals, but the actual, physical structure underlying everything we have ever known. Every star that has ever warmed a distant world. Every galaxy that has ever turned slowly through the darkness. Every planet, every atom, every quiet corner of existence, all of it connected, ultimately, to this same vast, patient architecture, woven together from dark matter's invisible gravity and ordinary matter's luminous glow, stretching across the entire observable universe. Somewhere above you tonight, whether visible through a clear window or hidden behind clouds and city light, that same cosmic web extends outward in every direction, filaments reaching across millions of light years, connecting galaxy to galaxy, cluster to cluster, in a pattern so vast that it encompasses everything we have ever managed to observe, and so ancient that its earliest threads began forming while the universe itself was still in its infancy. You are part of this structure. Every atom within you was forged within a star, gathered eventually into this quiet corner of one particular filament, within one particular galaxy, orbiting one particular star we call the Sun. The same gravity that shaped the cosmic web's grand filaments shaped, too, the slow formation of our own solar system, our own planet, and eventually, through countless generations of gradual change, you, resting here now, at the end of this long journey, carrying within your own body the quiet legacy of that same vast, ancient structure. Let that thought settle now, gently, as this journey comes to its close. The universe is vast beyond easy comprehension, its structures spanning distances and times that stretch far beyond ordinary human experience. And yet, within that vastness, there is pattern. There is connection. There is a quiet, patient architecture, woven slowly across billions of years, linking every galaxy, every star, every small and quiet corner of existence into a single, continuous, cosmic web. Rest now, within that connection, woven, as you are, into the same vast and patient universe we have spent this journey exploring together.